Hey everybody, so I'm Bryce Adelstein Lelbach. I work on the C++ programming language. That's what I'm here to talk to you about today. So I'm the chair of the standard C++ library evolution group, which designs and standardizes the C++ standard library. So any problems that you have with the C++ standard library, you can blame me for that. I also chair the American Committee for Programming Language Standards, and I serve as the editor for the Insights Inclusive Terminology Standards and Guidelines. I work at NVIDIA, where I'm a principal architect, where I drive our strategy for HPC and quantum programming models, C++ compilers, and C++ libraries, and I do a lot of things around open source and standards. So work on the next C++ standard, C++ 23, is nearly done. It's feature complete and nearly finished. We'll finalize it in February of 2023. And there's a lot of exciting changes that are coming in C++ 23. To name a few, there's a bunch of enhancements and additions to ranges, which we first added in C++ 20. There's new formatted output facility called std_print. We now finally have a proper multi-dimensional array abstraction in C++ called MDSpan. We have expected, which is this whole new error reporting paradigm. Standard library modules and deducing this and a bunch of other features and fixes. But I don't actually want to talk about any of those today or anything that's going into C++ 23. I want to look a little bit beyond C++ 23. I want to talk about 3 features that we're working on that I think we'll see in the language in the next 3 to 6 years that I think are going to really revolutionize how we write C++ code. And those features are reflection, pattern matching, and senders. So let's start off with reflection. So metaprogramming is the craft of creating or modifying programs as the product of other programs. Reflective metaprogramming is metaprogramming that incorporates data from the program that's being modified. So we've been able to do metaprogramming in C++ for many years, but what we've not been able to do is do that reflective metaprogramming. And that's what we're looking at adding. So there's 3 components that you need for reflective metaprogramming. First, you need some reflection mechanism, a way to extract information from the program. Then you need some compile time programming facilities that you can use to manipulate and transform that information. And then finally, you need injection, a way to insert new program entities from that compile time programming that you've done. So let's look at a simple example here. This is a function using the proposed reflection facilities that would take an enumerator and return its name as a string. Anybody who's got an enumerator and an enum in their code base probably has written one of these functions out by hand for every enum that you have. Now we're going to use a few different new C++ constructs here, and I'll walk you through them. The first is the reify operator. The reify operator takes a C++ entity, so a function, a struct, an enumerator, a variable, a namespace, and produces a reflection. So a reflection is a handle to an internal compiler representation of whatever we're reflecting on, in this case, the type T. So it's a C++ object that we can manipulate and work with like any other C++ object. So these reflection objects, they are of this std meta info type, which is this special magical type that the compiler exposes. Now, these reflections can be manipulated and transformed just like any other C++ objects. So here, we are passing the reflection of the enum type T to the function meta members of. And meta members of is going to return a new meta info object that will represent all of the enumerators of T. And so such a meta info object is a range. And so we can use a range-based for loop to iterate through all of the elements. And we want to use a special type of range-based for loop, in particular this template for construct, which is this new compile time expanded range-based for loop. So each element that we're dealing with here might be a different type when we're working with reflection data. And so a normal for loop wouldn't work. We want something that's going to sort of unroll itself at compile time. This is the sort of the equivalent of writing a bunch of if statements one after the other. So in each iteration of this compile time for loop, we want to check if the enum parameter of the function is equal to the value of the current enumerator that we're reflecting over. So to do that, we take the reflection of the current enumerator, and we want to turn it back into a real entity. And to do this, we're going to use another new operator, the splice operator. And the splice operator takes a reflection value and turns it back into the entity that it represents. So in this case, it will be the enumerator in question. So if the parameter is equal to the current enumerator, then we need to return its name. And we can get that name with another function that operates on reflections, meta nameof. So here's another example. This is a simple hash protocol. So this function, hash append, takes a hasher object and an object to hash. And it's then going to reflect upon that object that we're hashing, and then it will recursively call itself on all the data members of that object. So you can do this for things like hashing. It's also quite useful if you're doing something like serialization. We can imagine even more powerful facilities for injection. For example, if we could use this template for at class scope, then we could write classes that wrap and forward all of the methods of their subject class. So here I've got this traced class, and traced takes some object, and it will replicate all of the methods of that object and the signatures of all those methods. And when you call one of those methods on the traced object, it's going to call the underlying method on the wrapped object. But before it calls it, it's going to print out that it's calling the name of this particular method. So this is an easy way to add some instrumentation to a particular class. It's like I want to get a log whenever any method of this class is called. Well, I can do that pretty easily using this reflection facility. So I think that reflection is going to really fundamentally change how we write C++ code. Reflection will help us solve problems that today often require a lot of boilerplate, macros, or external code generation, or just things that are just very repetitive tasks, like having to write a function for every enum that we create that prints out, that gives us the string name of the enum. So this is going to be useful for things like serialization, protocol and language bindings, instrumentation, logging, debugging. There's a wide range of uses for reflection. I think it's going to really change not only how we build and design libraries in C++, but also how we evolve the language itself. I think that it's something that we'll use a lot in future C++ language evolution. So now let's move on to pattern matching. So C++ today has two types of selection statements. Switch operates on a single integral value. And this is often too limited. You can't use a switch to switch over string literals or objects. Now, if statements, on the other hand, operate on arbitrary Boolean expressions. So they're very powerful. You can do whatever you want with them, and they can express almost anything. But they're often too complex and verbose for a lot of the common cases. What we really need is something that's sort of in between the two. We need a powerful but concise way to select and decompose objects. And that's what we'll be getting with inspect, which is a new selection statement that we're planning to add to C++. So inspect matches values against patterns and then binds variables when matches are successful. So inspect is an expression, not a statement. And an inspect expression takes a parameter, which is the object that we're going to select against. And then it takes a series of patterns. And there's a variety of different patterns that are available. I'm going to highlight a handful of them today. So each pattern is followed by a statement, which is taken if the pattern matches. Inspect stops at the first match, not at the best match. So whichever the first one is that it matches, that's the one that it will take. So constant patterns are pretty straightforward. They just match if the object is equal to the constant. We also have the wildcard pattern, which is 2 underscores, and that will match against anything. Now, constant patterns aren't limited to integrals or enums like switch case statements are. They can work with strings or actually any arbitrary constant object. So here's another example. This is Fibonacci written with inspect. So here we're using another pattern, the identifier pattern. And the identifier pattern will bind the value to a particular name. There's also this thing called pattern guards, and pattern guards can be used to perform arbitrary tests to see if something matches here. In this case, we're checking to see whether or not the value is so large that it would cause an overflow error. So since C++ 17, we've been able to destructure tuple-like objects. And now we can do that in Spect 2 with these compound patterns. And so compound patterns would be a composition of any other type of patterns here. And this is very useful when we're working with tuple-like objects that we want to decompose as we're selecting them. Alternative patterns can match different types in variant or any-like objects, so something that's union-like that could be, an int or a float or a variety of different things. There's also extractor patterns, which allow us to completely customize how matching and decomposition is done by implementing our own extractor protocol. So Inspect gives us a powerful new way to select and decompose objects. It makes working with tuple-like and variant-like objects far more natural in C++. And I think it's going to really revolutionize how we write C++ code. I think this will become a very natural thing that we'll reach for almost any time that we're doing conditional logic, because it's very simple and it's a lot more natural than writing a bunch of if statements or writing a switch statement. Okay, so finally, let's talk a little bit about asynchrony in C++. So today, C++ has no standard model for asynchrony and no standard way to express where things should execute. And that's why we're introducing senders, which is a model for asynchronous execution in C++. There's three key concepts in the sender model. First, you have schedulers, which are lightweight, non-owning handles to execution contexts. Schedulers produce senders. Now, senders represent asynchronous work that will eventually send a signal. And a signal could either be success and some set of values that's produced by the work, failure and an error produced by the work, or cancellation. Now, you can take these senders and you can compose them together with sender algorithms to form task graphs. Receivers are connected to senders and process their asynchronous signals. So let's look at a simple example. So first, we need to get a scheduler from somewhere. This could be from a thread pool, from a tasking system, from a GPU driver, etc. And then to start a chain of work on the scheduler, we'll call schedule on it. And that will return to us a sender. And that sender will complete on the execution context that's associated with that scheduler. Next, we're going to use a sender algorithm then to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm then is going to return a new sender, which we can then use to add more work onto that chain. And there's a whole bunch of other sender algorithms which you can use to do things like fork and join and all sorts of other complex execution patterns. So then finally in this example, we're going to wait until the chain of work has completed using sync wait, which will return the value that was sent by the final sender in this chain. So there's also this pipe syntax for senders that gives us a nice clean way to compose chains of senders together in the order that they will be evaluated. So we've developed a prototype implementation of senders at NVIDIA that supports CPU schedulers, GPU schedulers, and distributed schedulers. So I'll show you a couple examples. So this is a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. And this is the entire solver loop, which is expressed as a graph of senders. And this code can be run with a variety of different schedulers. So by changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on a CPU using something like OpenMP or a thread pool, to running on a single GPU, to running on multiple GPUs within a single node, and to multiple nodes scaling up to thousands of GPUs. We've ported a simulation from the Palabos fluid dynamics framework to Senders. This simulation models carbon sequestration techniques. So the porous structure that you see is sandstone saturated in salt water. The red bubbles are liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. So using a distributed GPU scheduler, we've been able to run this application on up to 512 GPUs. So the whole idea with these standard C++ senders is that you can write your code in a way that is agnostic of where it's going to run, and then by just changing one line of code, the type of scheduler that you plug in, you can go from running on a single CPU thread to scaling up to an entire cluster of GPUs. Okay, so we talked about three things today: reflection, pattern matching, and senders. And I think these are the three most exciting things that we have on the roadmap for C++. And combined, I think that they're going to really change how we'll write C++ code and allow us to elegantly solve some of the problems that are today pretty challenging to deal with in C++. So that's all that I've got today. So thank you for your time and attention. Come find me later if you want to learn more or get involved in the development of C++. We've also got another session that'll be sort of a more informal like Q&A with me and another member of the C++ committee. And you can also check out my other talks on YouTube and my podcast, ADSP. And follow me on Twitter, I guess.